Hello, you're listening to the Science of Everything podcast, episode 57, Electric Current and Circuits. I'm your host, James Fodor. In this episode, we're going to have a more detailed look at some basic electrical phenomena, including electric current, voltage, resistance, and electric power, and then we'll apply some of these basic ideas to the analysis of circuits, including series and parallel circuits. We'll also talk about some other more applied phenomena of electricity, including light bulbs, how they work, lightning, and why electricity can be dangerous. Strongly recommend that you have listened to episode 43, Electric Forces and Fields, before you listen to this one, because I'll be assuming some basic understanding of what electricity is and, electric charge and things like that. So let's jump straight in. First of all, we'll look at basic electrical phenomena, starting with electron motion and electric fields. So when we turn the switch on an electric circuit, an electric field is immediately felt by all of the electrons or all of the charged particles. It doesn't have to be electrons, but usually it is, along the circuit path. Now, I say immediately. Technically, the field propagates at the speed of light, so it's only felt at the speed of light. But for most practical purposes, that's effectively infinite from for short distances over the Earth. So basically, it's felt immediately by all the electrons around the circuit. However, in response to feeling that electric field, and remember, if you don't know what an electric field is, look back at episode 43, even before you turn on the field, electrons are constantly jiggling around due to thermal motion. And then when you turn on the field, that introduces a slight overall bias in this random motion of the electrons, so that they're still jiggling around and going all over the place, but on average they move slightly more in one direction, in the direction that the field is pushing them, than in the other direction. And so it's not a case of like traffic flowing where you have a nice steady flow. It's more like, billiard balls bouncing around, but having a slight tendency to move towards the left over time. And this speed of slow movement over to one side is called the drift speed. And the stronger is the electric field, then the more rapidly will be the drift speed. Now, this drift of electrons or other charged particles produces what is called current, or electric current. The current is equal to the amount of charge that flows past a given point in a circuit over a particular period of time. So we just say that I, the current, is equal to Q, the charge that flows past the point, divided by the amount of time. So we talk about current as being an amount of charge per second, or coulombs, which is the measure of electric charge, per second. 1 coulomb per second is known as an amp, or an ampere. So that's an amp is a measure of current. The more amps you have, the more current is flowing past a given point in the circuit in a period of time. And another way of thinking about that is it means that you have more electrons moving past there in a given period of time. So that's all current is. It's just the flow of electric charge. Usually, again, when we think about electronic devices, it's electrons that are doing the moving, but it doesn't have to be. It could be protons or any other charged particles. Now, in order to have a current flow, you have to have two main things. First, you have to have a potential difference existing between 2 points. Basically, that means you have an electric field existing, a net electric field. Second, you have to have a continuous conducting path existing between the two regions. A conductor is some substance that allows the flow of charged particles. So wood, for example, is not a conductor because it does not allow the flow of charged particles. It doesn't allow electrons or protons to move through it freely and therefore carry current. But metal is a conductor because of its structure is different from wood, such that it does allow the passage of charged particles. It allows the charged particles to move from one part of the metal to the other, therefore current can flow. So again, to have an electric current, you have to have a potential difference existing, which relates to the electric field. It's not exactly the same as the electric field, but we'll get to that. And second of all, you have to have a continuous conducting path. You can't have breaks in the conducting path. This is important. Everyone knows that if you have a circuit in a wire and then you cut the wire, then the circuit is no longer complete and the light bulb goes out or whatever. You have to have a continuous path for the current to travel, because otherwise, essentially, it gets blocked up. It's like a traffic jam in a road. If you break the road, the traffic can't flow, and then you have a bank up and the traffic stops. So similar idea of electricity. You have to have a complete conducting path. And I suppose the third thing you need is a source of electric power, or of electromotive force is another way of saying it. We'll get to that in a moment. Basically, you have to have somewhere where the electrons are coming from, or the other charged particles are coming from, because if they're continually moving to the left, then you have to have some source of them. Otherwise, you'll use them all up and the charge won't be able to flow anymore. Effectively, that's what happens when a battery runs out. It runs out of charge, and there's no more electrons that can come, and therefore no more current can flow. Liquids can also generally carry current. So water is famously a pretty good conductor of electricity. That's because there exists in water, or in most water, there exist electrolytes, so charged particles that are dissolved in the water. Also, the water itself dissociates into hydrogen and hydroxide ions, and we talked about that in the episode on acids and bases. where the H2O breaks up into O minus and breaks up into OH minus and H plus, which are ions, and therefore those can flow and carry charge. So water is generally a pretty good conductor of electricity. Gases can also carry current as well, so it doesn't have to be solid to carry current, although that's usually what we think of. By convention, and this is quite confusing, charge flows in the direction that positive charges move. That might sound reasonable enough, but remember, most of our electronic devices run on electron motion. So if you see the electrons are moving from left to right in a wire, that means the current is actually going from right to left. It's going in the opposite direction to the electrons. So that gets really confusing in electrical engineering and other fields like this, where you always have to remember that the current is flowing in the opposite direction to that in which the electrons are moving. And the reason that's the case is because current was described and defined before electrons were discovered. And so it wasn't known that the electrons were moving in a particular direction. It was just known that the current was moving in a particular direction. So they couldn't tell if the positive charges were moving in one direction or the negative charges were moving in the other direction. To put it differently, you can carry a charge from left to right. You can carry a current from left to right if you have either positive charges moving from left to right or negative charges moving from right to left. It's the same thing from the perspective of the electrical phenomena. It doesn't matter. And so at the time they defined current, they didn't know which was happening, whether it was positive or negative charges that were carrying the current. We now know that it's usually negative charges, and therefore we're stuck with this, what's called conventional current, where the current is defined as flowing in the direction in which positive charges would flow, which is the opposite direction to that in which the negative charges are actually flowing. So you just always have to remember that if you're dealing with circuits, that there are two types of current that we normally talk about: direct current and alternating current. In direct current, there's a unidirectional flow of electric charge. That means the electrons start at one side, they start to the right and they move over to the left, and they keep moving in that direction just forever, or as long as the charge is flowing. Now remember, they don't move straight in a straight line. They're always jiggling around, and there's some sort of overall drift speed. But in direct current, the drift speed is always in the same direction. Direct current is provided by sources like batteries, and solar cells are two common examples that provide direct current. The other type is called alternating current, and its initials are AC as opposed to DC for direct current. So if you've seen AC, DC, not the band, I mean AC or DC on some sort of electrical device, that's what it's referring to. So laptops, for example, they used, well, I think all computers actually, but certainly laptops use direct current. Their batteries provide direct current, but if then you want to plug it into the wall and charge it up, the wall provides alternating current. That's called mains electricity, or mains power in, all countries that I know of uses alternating current. What that means is that the direction that the electrons are moving in periodically changes direction. It swaps directions constantly, and it actually does that like 50 or 60 times a second. So if you see somewhere about the 50 or 60 hertz of mains power, that's what it's talking about. It's talking about how many times a second the direction that the electrons are going in is flipping around. 50 hertz is 50 times a second, and 60 hertz is 60 times a second. Most countries are either 50 or 60 hertz. So when you plug in your laptop to recharge it, it needs to convert that alternating current that it gets from the power socket to direct current that it uses to charge up the battery. And so that's what those big black rectangular things that you have on your laptop chargers are. That's a converter from alternating current to direct current. Well, I think they usually are. Maybe there are some chargers that are built differently. I don't know, but certainly for mine, that's what it is. It's if you read the label, it should tell you like what voltages it accepts and what voltages it outputs and things like that. So you can take a look at that and illustrate some of the concepts we're talking about. Now, you might be wondering how, or at least I wondered this when I learned about the difference between direct and alternating current. Okay, it kind of makes sense if you've got electrons moving in that direction, then we can use that motion to do useful stuff with. But how does it work if they're moving in, if they move to the left and then back to the right and then back to the left? They're constantly sort of jiggling around. How does that actually help anything? Like, how can we use that for anything? Because they're not actually, it's sort of like if we got in a car and then drove 10 meters to the left and then 10 meters to the right and then 10 meters to the left, there'd be no point to that, would there? You wouldn't get anywhere. Well, the important thing to understand is that for most purposes in using electricity, we don't actually need the electrons to get anywhere. There are some exceptions there, but like when you're doing electroplating, but in general, you don't need the electrons to actually get anywhere. You just need them to be moving. So it doesn't matter which direction they're moving in as long as they are moving in some consistent direction. So all of the electrons, or most of them, need to be moving to the left or to the right. It doesn't work if some of them are moving to the left and some of them are moving to the right at the same time, because then you don't have any net movement. You need to have net motion of electrons to the left or to the right, but it doesn't matter if 1 second or one fraction of a second they're moving to the left and then the next fraction of a second they move to the right and the next fraction of a second they move to the left again, as in alternating current. All you need is the motion, and it's actually the motion of electrons that we use to power electric devices, or many electric devices at least, particularly things like anything that is producing heat or running on a motor or something like that. And we can also get converters to convert from alternating current to direct current. If we need direct current for something like electronic devices, for example, we can just get a converter. So the reason that we use alternating current is because it's in mains power is because it's easier to transmit long distances, and we'll talk about that a little bit more in a moment. But that's enough on current, which remember is measured in amps, and now we'll move on to talk about voltage, which you've also probably heard of. Voltage, now it's important to understand current and voltage are completely different things. You can have high current and low voltage and high current. Well, they are related, but they are different things, and they're often confused. Voltage refers to the potential difference between 2 points, often in a circuit, but doesn't have to be in a circuit. One way of thinking about what this means is that the potential difference is the work that must be done or released, depending on whether it's positive or negative, moving a unit of charge between the 2 points. So a good analogy for this is thinking about gravitational potential energy, which I think we would have talked about in Newton's laws or something like that, maybe even episode 1 when we did understanding gravity. If I'm standing on a cliff, I have higher gravitational potential energy than someone standing at the bottom of a cliff, because in order to move from the top of the cliff to the bottom of the cliff, I have to give up energy. I mean, if I stepped off, I'd fall down and I'd accelerate towards the ground, and therefore I'm giving up gravitational potential energy and converting it into kinetic energy until I splat in the ground, and then it's converted into friction and heat energy and other things. But the point is, you can clearly see that someone standing on top of a cliff has more energy in terms of gravitational potential energy. In terms of how far could you fall, they have more energy than the person standing on the ground. It's the same thing with electrons, or any other charged particles. If you have an electric field, there can be electrons that are located at positions of high electric potential, and then those that are located at positions of low electric potential. Remember, opposite charges attract, so if I have an electron that's right next to a proton, that's pretty low energy, because it can't move it's going to be attracted towards the proton, but if it's already right next to it, then it can't really move any closer to it, it's already there. So that's low energy. That's like standing on the ground. But if I have an electron that's a decent ways away from the proton, if it's too far away, it won't even feel any force, but if it's a decent ways away from the proton, then it has some amount of electric potential energy, because it will be attracted to the proton, and as it moves towards it, it will lose energy, so it's giving up energy. Or, to think of it in the opposite way, if I wanted to move that close electron away from the proton, I would have to put energy in. I'd have to add energy to move that charge from near the proton to away from the proton. And so the difference in energy between the far electron and the near electron is called the electric potential energy. Now, there's a slight difference between electric potential energy and just plain old potential energy, but we're not going to worry about that difference. It's just too confusing. We'll just think of them as being basically the same thing. So the voltage refers to the potential difference, the difference in energy, or potential energy, between the particles the charged particles at different points around the circuit. Another way you can think about it is that electrons, so you have your battery with a positive and a negative terminal. Electrons will come out of the negative terminal and then travel along the wire, if you have it connected up to the circuit, and travel along the wire to the positive terminal. The reason they're doing that is because the potential energy at the positive terminal is much lower than at the negative terminal. You can imagine that there's a big bunch up of negative charge at the negative terminal. That's why it's a negative terminal. And the electrons are repelling each other, so they're pushing each other away. So that's a very high energy state, being in a bunch of other electrons. You want to move, if you're an electron, you tend to move away from that concentration of electrons. And if it's possible, you'd like to move around to the other side, where you can move towards a proton, which has a positive charge, and therefore you're attracted towards the proton. So that's a much lower energy state. You can't really lose much more energy once you're at the positive terminal there. So that's why electrons will tend to move around the circuit from the negative terminal to the positive terminal of the battery. And therefore we say that there is a potential difference between the positive and the negative terminals of the battery. That's a voltage. So the potential difference between the two terminals of the battery is the same thing as the voltage of that battery. So if you buy batteries that are, 6 volts or whatever it is, that's referring to the amount of the potential difference in terms of energy of a negative charge if you put it at one terminal compared to the other terminal. The higher the voltage, the greater the potential difference. And generally, high voltages translate into more energy or more power, or a larger current also. It's not always the case that higher voltages lead to more current, but sort of generally speaking. Another way of thinking about voltage is to think about it in terms of pressure. So if you had some sort of hose or pipe, and you had really high pressure, that corresponds to a high voltage. So voltage is kind of like pressure. It's the pushing. It's not the actual force. It's more like the potential push. If you have lots of water that is accumulated behind a dam, you have a very strong pressure there, that if you start to break the dam, you'll have a massive flow of water. But the water's not actually flowing because it's all built up behind the dam. that's similar to voltage in that you don't actually have to have a current flowing in order for there to be a voltage. Like if I pick up my battery, suppose it isn't plugged into anything, I'm just picking up the battery. There's no current flowing because there's no circuit there. It's just a battery. But I can still say that there's a potential difference across the two electrodes of the battery, of 6 volts or whatever. So the potential difference exists regardless of whether there's an actual current flowing. But you can think about it in the terms of potential difference means that there's a potential for current to flow. If you don't have a potential difference, you can never have current flowing. It's impossible. But if you do have a potential difference, then you could have current flowing if you set up a conducting circuit between the 2 points. So if I attached a wire to the positive and negative ends of the battery terminal, then I would have a current flowing. The current flows as a result of the pushing force of the voltage, but it doesn't actually flow until I allow it to have a conductive path. Hopefully that sort of distinguishes between the difference between current and voltage. Now, to bring them together a bit more, we discuss the concept of resistance. Electrical resistance refers to the opposition of a particular material to the passage of electric current. It's the inverse of what's called conductance. So if you have high conductance, you have low resistance, or if you have low resistance, you have high conductance. They're just opposite of each other. Resistance is kind of like friction, in that if you push something across a rough surface, you get lots of friction, so it doesn't move as fast. Similarly, if you have a certain voltage and push electrons through a conductor, the more resistance you have, the less current you get. And so there's this famous law in electric circuits, electronic engineering, or electrical engineering, known as Ohm's law. That's spelled O-H-M, if you haven't seen this before. And Ohm's law states that for linear resistors, so, I mean, not everything obeys this law, but for the moment we'll just abstract away from that and just pretend that everything obeys Ohm's law for simplicity. For things that obey Ohm's law, there's a direct linear relationship between current and voltage. So the algebraic version of the law is V, voltage, equals I, current, times R, resistance. Think about it in these terms. Another way of writing that equation is that the resistance equals the voltage divided by the current. So let's give a voltage, let's give 6 volts, say, and then connect up a circuit with using a particular material as a conductor and see how much current flows. If you get lots of current, that means you have low resistance, because the electrons are flowing around your circuit and there's not much friction or any obstacles preventing their flow, and so you get lots of current. But if you produce a low current, that means you must have high resistance because there's lots of impediments stopping the flow of electrons. At a sort of micro level, resistance is a result of electrons bumping into things, generally atoms, in the material as they are moving around the path. So different materials have atoms in different configurations and different arrangements of electron clouds and bonding and so on. And this means that the amount of times that electrons tend to bump into atoms or bump into other things as they try and move around the circuit differs depending on whether it's a conductor or an insulator or something else. So air is actually a pretty good insulator. It doesn't conduct electricity very well at all, whereas water is usually a pretty good conductor of electricity. Obviously, we know that metal is a very good conductor. Wood is not such a good conductor of electricity, so it depends on the material. Now, what happens if I took my imaginary battery once again and connected it up with, say, a copper wire? Everyone knows that copper wire is used in electronics because it is a very good conductor. It's also relatively cheap, although getting more expensive these days. So suppose I get my battery, I connect up the 2 terminals using a copper wire and nothing else. I just connect them up directly using a copper wire. We know what the voltage is. The voltage is the voltage of the battery, 6 volts or whatever it is. What will the resistance be? Well, the resistance is going to be very low, because I've just said copper has a small resistance, and I haven't put anything else in the circuit. There's nothing else to impede the flow of current. So how much current am I going to get? I'm going to get a very large amount of current. In fact, what will happen is, assuming I have a large enough battery and whatever, I'll get so much current that the wire will start to glow and become very hot, and my battery will run down very, very quickly because I'm using up all that charge. The battery only has a certain amount of charge in it, as we all know. Sort of what that means is there's only a fixed number of electrons that are available to move around. Once you've moved out all those electrons, there aren't any more to come, and so you can't have any more current flowing. Now, the more rapidly I draw current from the battery, the more rapidly I'm pulling off those electrons, and so the more rapidly they're used up. And so if I have this wire connecting my 2 terminals directly without any other what we call load on the circuit, so I don't have any light bulb or anything else in there, then I draw a very high current, I deplete the battery very rapidly, the wire heats up, potentially causes a fire, and we get what's called a short circuit. So this is a short circuit, when you connect up the 2 terminals of the battery or 2 ends of a circuit without any load to dissipate the energy in between them. It's a big fire risk, short circuits, because the wire can heat up so much that it can cause fires. So that's one reason why it's important to insulate electrical devices, is to try and prevent short circuits, which can cause fires and damage the electric components as well. Okay, one final concept, electric power. Now, in everyday language, we use the word power just to sort of mean ability to do something, like you're a powerful person or superpowers or something like that. In physics, electricity, power has a very specific meaning. It's defined as the energy used or transformed per unit time. So eon t, if you want to think about it in algebraic terms. Now, the energy, it turns out, is equal to the amount of electric charge multiplied by the voltage. Hopefully this kind of makes sense, because the voltage is sort of like the energy per charge. It's sort of like how high you're standing. Then you multiply that by the number of charges that you have, and you get the total amount of energy. So voltage is energy per charge, you times it by the number of charges, you get total energy. You divide that by the amount of time that's been taken to generate that energy or transform that energy, and you get the power. So power is the amount of energy per unit time. It's measured in a unit called watts, which is joules per second. Joules are a measurement of energy, joules per second is a watt. So it's a rate of transformation of energy. You've probably heard of a kilowatt hour, or maybe a megawatt hour. Kilowatt hours are generally used to describe the amount of electricity that a business or a household has used in a month or a week or however often you pay your electricity bills. This is well, in my view, and anyway, it's a rather odd unit because, remember, a watt is just a joule per second. So if you're using a watt, it means every second you're using a joule of energy. Old incandescent light globes, well, not so old ones, but not the newer versions, but the older versions of incandescent light globes, the traditional ones, many of them were maybe 100 watts or 80 watts or something like that. So that means they used 100 joules every second. A kilowatt is just 1,000 watts. Kilo just meaning 1,000. If you're using a kilowatt, that's like 10 100-watt light globes all plugged in and running at the same time. So remember though, a watt is not an amount of energy. It's the rate of energy used per time. So every second, that's 1,000 joules, 1,000 joules, 1,000 joules if you're using 1 kilowatt. But when you take a kilowatt and multiply it by hours, that then becomes an amount of energy because you've taken energy per time and multiplied it by some time unit. So a kilowatt hour is not a rate of energy use anymore. It's gone back to being an amount of energy. But that's kind of weird because what we've done is we've taken an amount of energy and then divided it by time and then multiplied it by time again. So saying kilowatt hours is kind of like saying joules per hour every hour. It's sort of weird to do it that way. I'm not exactly sure why it's done. It would make more sense just to say joules because kilowatt hour is just the same as joules in the sense that they both measure energy. 1 kilowatt hour does not equal 1 joule, but you can convert directly between them with the simple conversion factor. Anyway, a kilowatt hour is a measurement of the amount of energy that you use. And you can often find out how much electricity an appliance uses by looking at its electricity usage. Look at it and it'll tell you X number of watts. So you can compare that to a light globe. Light globes these days don't use like 60 watts because of new energy saving technologies. I don't know, they use like 10, 20 watts or something like that. You can, again, just look on them and it'll say how many watts it's using. And then you can compare that to whatever appliance you're thinking about, whether it's your toaster or your fridge or your microwave oven or your air conditioner or whatever. And you can compare how much energy each appliance is using. So that might be something interesting to do to apply your new knowledge. And remember, that's saying how many joules that appliance uses every second it's turned on. Now that we've discussed all the basic ideas, let's talk more specifically about electric circuits. An electric circuit is a device, or perhaps a system of devices, that provides a potential difference, a voltage, that allows a current to flow around some sort of system. A circuit exists whenever you have a conductor connecting two ends of a device that produces what we call an EMF. EMF stands for electromotive force. And it's a really bad name because it's not a force. Electromotive force is just the same as a voltage or a potential difference. So they're all basically the same thing. So if you have any device that produces a potential difference, and you connect that up to a conductor, then you have a circuit. That's all you need to have a circuit. So an example of a device that produces EMF is a battery. Another device that produces an EMF is a generator, one that runs on petrol or one that runs on coal or whatever. Another example of an EMF generating device is a solar panel, a photovoltaic panel, etc. The way I think about an electromotive force or a voltage is that it's just a build-up of electrons somewhere at some point, and therefore the electrons tend to be pushed away from that point, therefore you get the voltage. You get a potential difference in energy between 2 points. So that's what we do fundamentally that's what we have to do to generate electricity. You generate a build-up of electrons somewhere, and then get them to flow around a circuit, and there's your electric current, and that's a circuit. Now, circuits generally include more than just conductors and sources of EMF, because if you just had those two things, it wouldn't be very interesting. Generally, we then add other components that do interesting things like resistors, inductors, capacitors, switches, and other things like that. We won't talk about too many of those things now, because they're a bit more advanced, but it's important to know that there are names for various other components. Now, when we're analyzing the behavior of circuits, there's two big laws that you need to know, and they're called Kirchhoff's laws. That's spelled Kirchhoff, sort of a weird spelling. I think it might be a Russian name or something like that. Anyway, there are two laws, Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law says that the sum of all the currents entering a node, now a node is just some component of the circuit, it could be a light bulb or a junction of wires or anything like that. So the sum of all the currents entering a node is equal to the sum of all currents leaving the node. So imagine if I have one wire, which then branches out like in a Y shape into two wires. That tells me that if I have 1 amp running into the Y, I have to have a total of 1 amp running out. I can't have 1 amp running in and 2 amps running out, because then I've got more current leaving than coming in, and therefore I have, where am I getting those electrons from? That's impossible. Or to put it differently, if you did, that means there's some sort of source of electrons there, in which case you're not analyzing the circuit properly. So Kirchhoff's current law is just another way of saying that electric charge is conserved. You can't create it or destroy it. It has to always be maintained about the circuit. So if you have wires branching out and the current is distributed across them, then each of those wires has less current than the initial wire did. Or conversely, if you have wires converging, if you have 5 wires converging into a single wire, then that single wire has more current flowing through it than the 5 wires that contribute to it. So than each of the 5 wires that contribute to it. You add up all the 5 wires and you get the same current as you have in the single wire. So that's Kirchhoff's current law. Kirchhoff's voltage law says that the sum of the potential differences around any loop in a circuit, around any single closed loop, must be 0. Now this is effectively a way of stating the conservation of energy. If this wasn't the case, then what you could do is you could start an electron at a certain point in the circuit and then move it around once, and then say it gained a little bit of energy. So say instead of adding to 0, the voltage is added to 1 volt or something like that. Well, that means by moving it around once, it gained energy, or maybe it lost energy. It doesn't matter. And then you can move it around again, and it gains or loses energy again, and then you could just keep moving it around. If that were possible, you could create a perpetual motion machine by just a perpetual motion device by just moving the electrons around forever and ever and ever, continually gaining or losing energy. But that's impossible because you can't create or lose energy. So in any actual closed loop in any real circuit, the sum of the potential differences is always 0. So think about a simple circuit where you have a battery that produces 6 volts of potential difference connected up via wires to a light bulb, say. Now, what's the potential difference across the battery? Well, we know it's 6 volts because that's the potential difference between the two terminals. What's the potential difference across the rest of the circuit, excluding the battery, just the conductors and the light bulb? Well, we know it has to be 6 volts, or you can think of it as sort of positive 6 for the battery or negative 6 for the wire around the circuit, or you can flip the signs around, it doesn't make any difference. But the point is they have to add up to 0. So positive 6 in one, negative 6 on the other, they add to 0. So in other words, you can think about what the battery does is it pushes the electrons uphill, giving each charge 6 joules of energy, and then once the electrons leave the battery, they sort of gradually fall downhill, and over the course of flowing around the circuit, they lose energy until by the time they get to the other end of the battery, they've lost all 6 volts of energy, or 6 joules of energy per unit charge, that they had gained, that they had been given by the battery. So by the time you get back to the end of the circuit, they're back to 0 again. So you always have to balance out at the end there. Any closed loop in a circuit the voltages must sum to 0, because again, if that was not the case, you'd be violating conservation of energy. So those two laws are the basic conceptual underpinning that is necessary for basic circuit analysis. Although we won't actually do circuit analysis because it can get a bit tricky, but if you understand those points, then you understand a fair bit about the behavior of electricity, because they come directly out of the fundamental physics. It's just conservation of charge and conservation of energy is really all that's underpinning Kirchhoff's laws. Okay, now something else you may have heard about is series and parallel circuits. They're different types of circuits, and it's useful to understand how they behave and why they're different. So, to explain the difference, just imagine we have, again, our circuit that has a battery and then 2 light bulbs. We're adding a second light bulb now. When we're adding the second light bulb, there's 2 ways we can wire up this circuit. We can either put them in series or we can put them in parallel, the light bulbs, that is. So let's imagine putting them in series first of all. This means that you just put the light bulbs next to each other. That is, we have the wire coming out from one terminal of the battery, and then we whack in a light bulb, and then the wire continues on, and then we whack in a second light bulb, and then the wire continues on from there, and eventually comes back to the other terminal of the battery. So they're just sitting next to each other with the wire flowing through them, sort of in a continuous circuit, so that if you were an electron flowing along the circuit, you would first come to the one light bulb, and then you would pass through that light bulb, and then you would eventually get to the second light bulb and pass through that. So every electron that flows through the circuit must pass through both light bulbs. That's what a series circuit looks like, where the components are next to each other so that the current flows through all of them. When you have components connected in series, they all have the same current. The same current must flow through all of them, because remember, the same number of electrons flows through all of them. But the voltage may be different, because the voltage refers to the potential drop or the potential difference on each side of the component. So, for example, and we know that the potential difference depends on the resistance. If current is fixed, then voltage depends on the resistance. So suppose I have two light bulbs, and one of them is rated at 20 watts and the other one is rated at 5 watts. Well, that might well be because when you run the same amount of current through them, they have different resistances. And so that means that, consider the 6 volts that I have for my battery. That I've got 6 volts to spend as an electron as I go around my circuit. Flowing along the copper wire does not expend very much energy at all, because remember, the resistance is so low, so I hardly lose any voltage going through the copper wires. When I get to the first light bulb, let's say I spend 1 volt, or 1 joule, per unit charge. I spend 1 volt of potential energy. That means I must spend 5 volts on the second light bulb, because it has to add up to 6, assuming that the copper wire is negligible in terms of how much voltage I spend on that. If I spend 3 on one, I have to spend 3 on the other. It has to add up to 6, but they don't necessarily have to be the same, because the potential drop depends on resistance, and the resistance of the 2 light bulbs doesn't have to be the same. If the 2 light bulbs are identical, you just get 2 versions of the same, you buy 2 of the same thing, then they will be the same. But if they're different components, they're made out of different materials or something like that, then their resistances might be different, in which case the voltage drop does not have to be the same over both of them. So, let's just imagine, though, that I get 2 of the same type of light bulb and plug them into the circuit, wiring it up in series. What I will find is that, compared to the circuit that only has 1 light bulb in it, I actually have less current flowing through the circuit, and the battery lasts longer. So this might seem weird. I've got 2 light bulbs instead of 1, but my battery actually lasts longer. Then how does that work? Well, the reason is the total resistance of your second circuit with the 2 light bulbs is bigger than the total resistance of your first circuit, because you've added more stuff for the electrons to collide with. Particularly, you've added the extra light bulb. So the total resistance increases, and therefore the total current decreases. And if both of your batteries have the same number of electrons, the same total amount of charge that they hold, but one of them you draw out more current, the other one you draw out less current, clearly the one you draw out less current from is going to last longer. Just like if you have 2 buckets the same size and you pour one out rapidly, you pour the other one out slowly, then the one you pour out slowly is going to last longer. It's the same basic principle with the batteries. So that's why if you connect up bulbs in series, each bulb will get dimmer. It won't be as bright because there's less current flowing through the entire circuit, and the battery will last longer. Another important point about a series circuit is that every device must function for the circuit to be complete. Because remember, the electron has to flow through the first light bulb and then the second light bulb. It has to flow through both of them. So if you have 10 light bulbs lined up, then the electron has to flow through every one of the 10 before it can get back to the other terminal of the battery. So if even one light bulb blows and the circuit is broken, then all of the light bulbs turn off, because you no longer have a complete circuit. So if you have a bunch of lights that are connected in series, and you find they're not working, that could just mean that it might mean that the whole thing is broken. It could just be a single bulb has gone, and therefore the whole circuit of lights no longer works. And so therefore you have to go through the tedious process of looking at every light bulb and figuring out which one has blown. So generally, more expensive ones will probably be wired up in parallel, which is what we'll talk about next. So parallel circuits are different to series circuits. Remember, in series circuits, you've got all the components next to each other, and the electrons have to flow through all of the components to get around the circuit. In parallel, it's different. They're not sitting next to each other, they're sitting, sort of parallel from each other. So in a sense, what you have is that the copper wire flows out of one terminal of your battery, and then it reaches a fork. It can go down path A or path B. On path A will be our first light globe, and on path B will be our second light globe. And if we had 10 light globes on the circuit, then there'd be 10 forks in the road. Or another way of thinking about it is, you can think about the electron driving along the road, and then it reaches an intersection where it could turn off to the right and go through light bulb A, and then it decides, obviously it doesn't really decide, but it decides not to go down the turnoff, and then it keeps going, and then a little bit later it reaches a second turnoff where it could go down and flow through light bulb B, and on for each of the 10 light globes. So in a parallel circuit, the electrons only flow through one of the light globes, not both of them. This means that the amount of current does not have to be the same for each of the light globes, because you could have lots of electrons going through one passage, one of the turn-offs, and not many of them going through another one of them. They could have different amounts of current flowing. And the amount of current that actually flows, of course, depends on the resistance. If the light bulbs are all the same, then you'll get the same current flowing through each of them. But what happens to the total amount of current that flows through the whole circuit? The total amount of current actually increases. Remember, in the series case, the total amount of current decreased because we increased the total resistance. Well, in this case, we've actually reduced the total resistance by putting in more light globes. Now, this might sound weird. How can we have reduced the total resistance this time when last time we put in an extra light globe, we increased total resistance, but this time we've reduced it? How does that work? Well, think about it this way. What we've done is provided more paths that the electrons can travel around. We didn't do that last time. We just put more obstacles along the same path. Now we're providing extra paths. And so what happens if you say build more road connections between two places? Well, then there's more routes for the traffic to take, and therefore each route is less congested. That's sort of the same idea that's happening with the electrons. Each route that the electrons can flow through is less congested, so total resistance goes down. There's less bumping into things as the electrons flow through. So when you add additional components to a circuit in parallel, total resistance of the circuit declines, and therefore you get more current flowing through the circuit. So in fact, if you connect up two light globes in parallel, the total current that flows through the circuit is doubled, and so therefore the battery runs out twice as fast. And also what you'll see is that each globe is just as bright as a single globe was if you only had one globe hooked up. And that's because the potential difference is actually the same. The potential difference over each of your globes is going to be 6 volts. Because remember, your electrons are going through the path separately. So imagine an electron going around the circuit through bulb A. How many volts does it have to lose? It has to lose 6. So that means the potential difference across this first bulb A, is 6 volts. And so it's 6 volts worth of brightness. Brightness is going to depend on the volts and also the current. And then what about an electron that's moving through bulb B, the second light bulb? How much potential difference does it have to lose? Well, again, it's 6, and so there's 6 volts potential difference over that bulb as well. So we have 6 volts of potential difference over both light bulbs, and therefore this differs from the first case where, remember, there was 6 volts of potential difference across both light bulbs, so 3 over one, 3 over the other. But in this case, in the parallel case, it's 6 over each. So the main difference between series and parallel circuits is whether or not voltage stays the same, but current splits, or whether current splits and voltage stays the same. So in a series circuit, the voltage is split across all of the components, and current stays the same over the whole circuit. Well, the current is the same for each component. The total current may change. Whereas in a parallel circuit, the current is split across the different components, but the total voltage of the individual voltage of each component is still the same. But because you're drawing a lot more power in a parallel circuit, the battery runs out more rapidly. However, the advantage of a parallel circuit is that if one component is removed or is damaged, then the entire circuit does not stop working. Only that component will stop working. So that's why in household circuits, components are wired up in parallel rather than in series. Because if you had every single power point in your house wired up in series, that would be really annoying, because it would mean you would have to have something plugged into every power socket and turned on, therefore drawing a current, in order to have any of them work, which would just be ridiculously inconvenient. So in practice, they're wired up in parallel, so that you can turn them each on and off individually. And also, each outlet is usually wired up in series with a fuse or circuit breaker, which is a device designed to break, and therefore break the circuit if the amount of current flowing through that portion of the circuit exceeds a certain amount. The way it works is effectively it's just a thin wire or something like that, which will blow out, which will literally be destroyed, like a light bulb that eventually breaks. The wire is destroyed when more than a certain amount of current flows through the wire because it overheats. And the reason you'd want to do that is because you want to prevent a short circuit or something else, or some sort of electric accident. If too much current is flowing through the wire, that means there's some sort of short circuit, and you're at risk of fire. Therefore, the fuse will blow, it will break the circuit, and current will stop flowing. So this is an example of a negative feedback device. If you get too much current, it causes less current to flow. Circuit breakers are better than fuses because you don't have to replace them. You just flip the switch and it's working again. But they fulfill the same purpose. This is why this kind of annoys me then in science fiction movies or action movies or whatever. If you see various electronic devices which have sparks going all over the place and people touch them and they get electrocuted or whatever, is very silly, because even if there was some sort of electric discharge or whatever, any of these devices should be wired up to a circuit breaker or a fuse, in which case it would be very much less likely to be for a person to be electrocuted by touching it, because the fuse would break and the current would stop flowing. But for some reason, they never seem to use circuit breakers or fuses in movies. I suppose because it's less dramatic. Anyway, before we finish, there are a few interesting applications of electricity which we will talk about. The first is how light bulbs work. Light bulbs are conceptually a very simple technology, although they're certainly very useful. Basically, all a light bulb is, sort of conceptually, is electrons flowing through a thin wire, thereby heating up the wire as they bump into things. You know, the resistance of the wire causes electrons to bump into things, thereby releasing energy in the form of heat. Heat's just molecules vibrating more rapidly. So the electrons come along, they bump into things in the wire. They cause they bump into things in the wire, that is atoms in the wire. They cause the atoms in the wire to vibrate more rapidly. That heats up the wire and causes it to raise in temperature. As the temperature of the wire goes up, it starts to glow. And if it heats up enough, it glows in the visible spectrum. This is just black body radiation, which we would have talked about at some point in the quantum mechanics episodes. Basically, anything will glow if it is raised to the right temperature. So all you have to do to get a wire to glow is raise it to the right temperature. How do you do that? Flow an electric current through it, electrons will bump into it, and it'll raise it to the right temperature, and you'll get visible light. That's the basic principle. Now, conceptually it's very simple, but in practice it's difficult to do, because you have to find a material that's not too expensive, and that is going to produce enough light, given a certain amount of current, so it has to be practical. You also have to have a way of preventing the filament, which is the small wire that actually heats up. You have to prevent the filament from coming into contact with other things, because, you know, the filament can typically reach 2,000 or 3,000 degrees, which is not quite enough to melt the filament, because the filament's usually made of tungsten metal, which has a very high melting point. So that the filament's not going to melt, but you don't want that 2,000 or 3,000 degree filament coming into contact with other materials, because you'll get fires and all sorts of horrible things going on. So you have to have some way of preventing that from happening. So generally what's done is in modern incandescent light globes, they have airtight glass enclosures. That's what the bulb is. It's just an airtight enclosure that surrounds the filament. It's often filled with some inert gas, or in the past they were also just made in a vacuum. And that's to prevent, you know, the air being ionized and other things like that happening. Also, one point on, so these sort of engineering difficulties of finding the right filament material and producing the bulb in the correct way and making it cheaply enough to mass produce meant that the light bulb took a long time to develop. There were many people involved in its development and eventual production over the course of the 19th century. The traditional story that Thomas Edison invented the light globe is, well, it's partly true, but it's more complicated than that, because many people worked on developing the technology over the course of the 19th century. Thomas Edison and Joseph Swan, who were two people working independently of each other in the late 1870s, were sort of both the first people to develop an efficient modern form of producing reliable incandescent light globes. But they weren't the first people to make any type of light globe, just the first people to make it efficiently and capable of being mass produced. So that's how electric light globes work. Oh, by the way, it's important to note that's only how traditional incandescent light globes work. That's the ones with the filaments and the sort of rounded bulbs. Modern lights, including fluorescent lights, LEDs, and other things, use completely different principles. So this explanation is sort of becoming increasingly less relevant as incandescent lights become more and more obsolete. Okay, a note on safety and electricity, or in other words, why electricity can be dangerous. So there's two main sources of harm that electricity can produce. That from Joule heating and that from disrupting the heartbeat. Joule heating just refers to the fact that when a current flows through something, it heats it up. That's precisely the same principle that allows electric light globes to work. The Joule heating heats up the tungsten filament, which then glows. So if there's a current that's flowing across your arm, then your arm is going to heat up through Joule heating, and then your arm gets hot and your skin gets burnt, and, you know, that's bad. So that's one source of harm from electricity. But probably the more problematic harm is the effect of the disruption of the electrical signals generated by the heart and other nerves. So as you probably know, the heart is an electrical organ. It engages in a pretty much a constant sequence of contractions, which pushes out the blood and pumps it around throughout the body, thereby delivering oxygen to all our cells and removing waste and such. But that sequence of contractions is generated by a sequence of electric pulses, which is produced by cells in a particular region of the heart. But the point is, if you run a current over these cells in the heart, it will disrupt the timing of those pulses, and therefore the heartbeat can be disrupted or become erratic, or in other words, you won't have a regular heartbeat. And of course, this is a problem because you need a regular heartbeat to survive. And now this is where we come back to a point which we discussed earlier about the difference between current and voltage. How dangerous an electric device is, or a given source of electric current is determined by a combination of the current and the voltage. If you have a lot of current but very low voltage, it's unlikely to do so much harm. Similarly, you can have very high voltage but only a low current, and it probably won't hurt you. So this is what happens with so-called static electricity. Static electricity is when there's a build-up of charge on some static object, and there's sort of you touch it and then there's a spark and you have a one-time flow of electrons, but it doesn't keep flowing, it's just a one-off thing. These are produced by Van de Graaff generators, for example, or when you rub your shoes on the carpet or whatever. But this type of static electricity can actually often have a very high voltage, like thousands of volts, but the current is exceptionally low because the total number of electrons that flow is tiny, because it just happens for like a fraction of a second, and then the electrons have all been used up and then there's no more charge to flow. So static electricity can have very high voltages, but very low currents, and therefore it's not very dangerous. So Van de Graaff generators really aren't dangerous because the current is just minuscule. And you need high current to really be dangerous as well. So that's why it's a bit misleading if you just talk about the voltage of something like an electric fence or something like that. That doesn't tell you how dangerous something is. You need to know what the current is as well. And the flip side to that is that you don't actually need very much current to disrupt the heartbeat. So even fairly small currents, in terms of hundreds of millivolts, I think, can be enough to disrupt the heart. So you need to be careful. Even relatively low voltages, if the current is sufficient, can be quite dangerous. So that's why, as an example, it's inadvisable to use electric appliances near water, because water is generally a good conductor of electricity. If you drop the electric device in the water, the charge can flow through the current can flow through the water and ultimately flows through your body. By the way, remember our bodies are mostly water, so if water conducts electricity, our bodies certainly conduct electricity, particularly if your skin is sweaty, for example. And then the electricity flows through your body, it flows across your heartbeat is disrupted, and if you're unlucky, you will die. So, advisable not to use electric devices in the presence of water. Another application of this is, depending on the circumstance, sometimes if someone's being electrocuted, they might be, say they've touched a live wire or something like that, they might actually be unable to let go, because, remember, in order to let go, you have to constrict muscles, which thereby, pull on tendons and move bones. But how does that occur? Well, that occurs by electrical signals, which tell the muscles to contract. But if you have a current flowing through your body, then the electric signals are not able to operate properly, and therefore potentially might be unable to contract the necessary muscles to move your arms and let go. So that's another reason why electricity can be dangerous. It's because once we're in contact with it, it can be difficult to move away. Also, if you know someone is in contact with a live wire, then you should never touch them, because then the electricity is just going to flow through you, unless you're wearing insulating clothing or something like that. Probably the best thing to do in a situation like that would be to find a way to shut off the current, if you're able to do that. Alternatively, if you do have to touch someone, then make sure you touch them with some sort of object or material which is insulating. So metal or body parts are not a good idea, because they conduct electricity. Okay, so one final thing that I want to talk about, which is lightning. Very interesting electrical phenomenon. A lightning bolt is really just a very large, rapid flow of electricity. It's basically a form of static electricity, just with really, really high voltages. The voltages are generated by activity in the cloud, which produces a buildup of charge in the cloud relative to the ground. You can also have lightning bolts which strike from cloud to cloud. So it doesn't have to be cloud to ground. It can also go from ground to cloud. So we often perceive of lightning bolts as originating in clouds and going to the ground, but it doesn't have to be that way. It can be the reverse, or from cloud to cloud. That's why you can sometimes have you just see the horizon sort of flashing. That's called sheet lightning. It's produced when you have bolts of lightning that are inside the cloud, so you can't see the bolt, but you just see the flash. There still is a bolt of lightning, you just don't see it. All of these lightning flashes are ultimately the product of potential differences which are produced between the cloud and the ground, or between two different clouds. As my understanding is, it's still not exactly understood how this buildup of electrons, or this potential difference, is produced. It's some sort of rubbing actions going on, but I don't think we understand exactly how that occurs. At least that's the last time I read about that. There might have been recent work that I don't know of, but I still think that's relatively poorly understood. But nonetheless, once the potential difference has been built up, then the charges will seek to equalize that difference, and so you tend to get what you have is that the air breaks down so that it separates out into charges, So for example, air molecules will break up into their component charged particles, and that allows the current to flow from the cloud to the ground, carrying with it a very large amount of energy. And accompanying that, you also have a very large increase in temperature as a result of Joule heating, as we discussed before. That in turn produces a rapid change in air pressure, because remember, when air heats up, it expands. That's the ideal gas formula. And that in turn produces a sound wave, which is heard as a loud crack, or we call it thunder. So there's actually a lot of interesting physics and science behind thunder. You have to understand about electric potential and electric currents, and you have to understand about air pressure and gases, and then how changes in air pressures result in us hearing sound. So there's, if you want to trace that whole process, it's quite interesting, all the physics at different points. The energy in a lightning strike is something in the range of 1 to 1 billion joules. 1 to 10 billion joules, which is quite a lot of energy. And energy is often released in a number of separate strokes within a few tens of microseconds. So if you watch a video of a lightning strike that has been recorded with a very high-speed camera, you'll often see that there's actually several distinct flashes within a very short period of time. You can't see that with the naked eye, but you can see it in a high-speed camera. It's quite interesting. You'll have those multiple flashes until the sufficient amount of the charge has been dissipated such that the potential difference has been mostly eliminated or significantly reduced, and then the lightning strike ends. Most of the energy is dissipated as heat, light, and sound, so that's why we see the flash. That's actually a result of electrons that have been ionized and then are falling back to their ground state. That releases light, and we see that as a flash. And the reason that it's not a straight line, by the way, rather than a path, is because the electric current's going to follow the path of least resistance, like literally wherever in the atmosphere the resistance is lowest. And so due to differences in air pressure and other small atmospheric effects like that, it won't just be a straight line between the cloud and the ground. It will be a sort of a circuitous path that goes around. And you'll see that, again, if you look at pictures of lightning, you'll see little forks that go off to the side and dead end and don't actually contact anything. That's sort of essentially a dead-end path that the electrons flowed there, but there's no ultimate circuit that forms, and so not much electricity flows through those things. The main electricity will flow down the main fork from the cloud to the ground, which is following the path of least resistance across that distance. Now, people have often suggested in the past that we should attempt to utilize all this energy that's coming in lightning strikes and store that power, and use that as a source of energy. It turns out it's exceptionally difficult to do that. One reason is because it's impossible to predict where lightning is going to strike, and you can't just have rods set up all over the place in the possibility that there might be a lightning strike there. That's prohibitively expensive and too difficult. Another difficulty is that the amount of energy is large, but it's delivered very quickly, and we don't really have, or it's difficult to build some sort of storage of electricity which will allow that much energy to be stored in such a short period of time. That's your laptop battery can't be recharged in a second. It takes hours to recharge. So it's a similar problem with the trying to store this energy of the lightning strike. Storing that much energy in such a short period of time is hard. But the main problem with using lightning as an energy source is just that there isn't enough of it. I did some rough calculations, and even if you could utilize 100% of the energy of all of the lightning strikes in the continental US in a given year, which is completely infeasible, but even if you could somehow do that, then you would only generate enough power to meet about 1% of the US electricity use. And, my figures are very rough there, but in practice, you would never get anything close to that amount of efficiency. So using lightning as a source of energy is really just not very feasible. It's too difficult, too expensive, and there's not enough of it. Lightning rods, you've probably seen before. These are just basically small conductors which are placed on tall objects, often buildings, sometimes trees, which serve to protect the building in the event of lightning strike. So the idea is that if the lightning is going to strike the building, it will preferentially strike the rod. Remember, follows path of least resistance, and the rod's closer to the sky than the rest of the building, and it's also a conductor, probably a better conductor than the concrete or whatever else the building's made from. So the lightning preferentially strikes the rod, and the rod it's actually not just stuck on the top of the building. That wouldn't help very much. It is connected up to some sort of wire or other metal structure which conducts the energy harmlessly into the ground. So instead of passing through the building, the energy passes harmlessly through this conductor and then is dissipated in the ground. And again, the purpose of this is to prevent the massive flow of energy from causing a fire or electrocution or other problems like that. Any object that is in electrical contact with the ground or with the earth is said to be grounded. That's the idea of grounding something. And the purpose of that is so that the energy will flow through the device to the ground, where it will dissipate instead of flowing through something else and causing damage. So that's the purpose of a lightning rod. Okay, so that's all we have for this episode. Hopefully you enjoyed it. If so, jump onto iTunes and give the podcast a favourable review. That would be much appreciated. You can also find us on Facebook, and also send me an email. My address is fods12@gmail.com, fods12@gmail.com. Even if you don't have any particular feedback or complaints or suggestions, I'd still just love to hear from you. I haven't received an email from a listener in a little while, but I do like to hear from you, so get in touch. Thank you for listening, and I'll talk to you next time.